Well, welcome again. You're probably wondering, where is this guy going with this? We've been talking about VSCPR for a while, and he told me it's wrong. When am I going to get to it? We're getting there, don't you worry. But we're going to build up some stuff a little bit more. Okay, so, and this is true for everything. Okay, so this graph here, if you look at the y-axis is potential energy. So negative in the bottom part, negative potential energy, that means more bonding. On the top, higher potential energy means they don't like each other. So that's too much potential energy. So the zero line, that's two atoms that are free. Now as atoms approach each other, they start to decrease in their potential energy and they bond. So there is this ideal length. And then at the same time, the atoms can get too close to each other and they won't like that. So kind of like when you shake someone's hand, right? So you go up to someone and you shake his or her hand. You're like, nice to meet you. Give a good handshake, But if the person keeps on coming closer to you, it gets uncomfortable. What if that person got into your face? You meet someone and then that person shakes your hand, responds, and then places his or her forehead on you and continues on and smushes your nose with his or her nose, and at this point it's really uncomfortable because you want to have space. You do not want to have someone pressing noses on each other till it's uncomfortable. Same works for atoms. They like to have this magic distance between them. They're close enough that they can share electrons, they can enjoy each other's company, but too close, what happens? The positive nuclei start to repel. So too far away, they can't bond. Too far away, they can't bond, they can't share electrons. Too close, the positive nuclei repel. The right distance, this magic distance, they actually share and they have good bonding with each other. That's what this graph is describing. That you have this magic distance, and that energy minimum is called the bond length for the distance, and the bond energy then for the decrease in potential energy. And okay, so we're going to come back and talk about valence bond theory. So this is true for everything. This kind of the magic distance there. But band theory, the idea of band theory is that this is trying to answer why things bond, is overlapping orbitals. And the next thing to talk about is hybridization. So if you look at carbon and hydrogen, these are their atomic orbitals, and they can. So if you were to try to bond carbon and hydrogen, you would think with the p orbitals it would form some sort of like flat square planar structure, but it actually is tetrahedral. Why? Because all tetrahedral structures form sp3 hybridized orbitals. Okay? So, well, according to the theory. And the molecular orbital theory actually is in agreement with this, so it does form these molecular orbitals, so this is true. And the idea is that these four atomic orbitals form these hybridized orbitals, and then the bonding would overlap in these bands. So that's the band theory. And valence band theory was in combination with VSEPR to describe bonding. And how do double bonds work? Well, there would be sp2 hybridized. So if you notice, all tetrahedral geometry is sp3 hybridized. Now, when it comes to planar geometry, it's sp2 hybridized. There is an unbonded p orbital, and then what happens is that these hybridize to form the planar molecules, and then these here form then a pi bond. So this is a double bond between them. So there's a sigma bond and a double bond. Okay, so what is a sigma bond and a double bond? And these are that sigma, that looking whatever looks like a golf club there. Sigma bond, that's lowercase sigma in Greek alphabet. So this is uppercase sigma, this is lowercase sigma. Okay, so sigma bond, And sigma bond means it is perpendicular to the internuclear axis. So you can't really see. So look at my fist and my elbow, okay? My forearm is the bond. The bond is then along this internuclear axis. This is a sigma bond. A pi bond is above and below. So a pi bond would be here and here between the internuclear axis. So formaldehyde here and between the carbon and the oxygen has a sigma bond here and a pi bond here and here. And it comes from the overlap of the p orbitals. And then, so with what? Well, with sigma bonds have free rotation. So kind of like your shoulder ball and socket in your arm. Okay, so this is free to rotate. Okay, it's real easy to do that. You rotate that, not a problem. What happens when you have a double bond? The double bond here, so single bond, this can move around fine. Double bond, though, you can't move this as much. You have to break the double bond to be able to move it. So double bonds hold things in place much better. So a double bond will prevent free rotation. And that's, again, why we have cis and trans. So you can see here that we mentioned cis and trans last class, where the cis is on the same side, trans is on the other side. Last class meaning last video. And so what? Well, this is how the light-sensitive cells in our retina work. So cisretinal. When a photo strikes it, it becomes transretinal, and then that sends a signal to our brains. So that is how our eyes work from cis to trans. Okay, so summary with this, that for linear electronic geometry, so this is electronic geometry. What I mean by electronic geometry, I mean for this chart here, remember this is the first video in chapter 10, the electron groups, all linear geometry, and I've written the hybridization there. All linear geometry has sp hybridization, all planar geometry has sp2, well, trigonal planar, I should say. For tetrahedral electronic geometry, sp3, for bipyramidal, sp3d, and octahedral, sp3d2. Okay, so that's what this is saying. This chart here describes then the geometry, and so the S and P is not listed in the textbook there, so I've drawn it for you there. Okay, so what is the bonding scheme for ethylene? So ethylene, it says ethene, that's the proper name. Ethylene is a common name. Ethylene is an interesting substance. Have you ever noticed this, that rotten fruit kind of smells similarly? You can take carrots and leave it in the fridge for a while. It's not even a fruit, it's a vegetable. You let it sit for a while, you'll smell something that kind of smells like, to me it smells like bananas. It has this kind of banana-like smell. If you let bananas sit for a while, it has it releases ethylene. So when fruit ripens, it releases ethylene. And ethylene is a compound, it's autocatalytic, meaning that as fruit ripens, it releases ethylene, which makes it ripen faster, which releases more ethylene, which is why you say, like, oh, one bad apple will spoil the whole bunch, kind of thing, because of that ethylene. Okay, so the ripened fruit will make the unripened fruit ripen faster and can cause them to spoil. That's also a reason why you put, if you want an avocado to ripen faster, you put it into a bag, because it traps the ethylene, and then it makes it ripen faster. And maybe you've had the joy of seeing, like, you get a banana, it's like, oh, it's all nice and yellow on the outside, and then you open it up, it's nice and raw in the middle, you're like, oh, man. That's because it might have been treated with ethylene. Okay, so ethylene, here's the Lewis structure for it. It is this. It's double bond carbon, two hydrogens. So what is the bonding with this? Well, it's planar, it's sp2, which means that there is an open p orbital here, and then the p orbitals can overlap there like that. So you can have a pi bond there above and below, and then a sigma bond between them. So the bond scheme here is planar geometry with one pi bond and one sigma bond. So if you notice, a single bond is one sigma, a double bond is one sigma and one pi, a triple bond is one sigma and two pi. If you go on and study more, you can learn about delta bonds. So you can have a quadruple bond. The d orbitals in certain metals can bond. You have then you would have one sigma, two pi, and one delta bond for quadruple bonding. So you can pause this at the appropriate time if you want to try this at home. What is the hybridization of sulfur and sulfur hexafluoride? It's octahedral, so it has that one. And nitrogen has how many pi bonds? Nitrogen is a triple bonded molecule with one sigma and two pi. And I've drawn a little prettier there for you. So there is my drawing of a nitrogen molecule. And actually, if you look at this one, you would think that nitrogen would look like a four-leaf clover kind of going through, but it turns out that the bonding scheme, the electron density in nitrogen is actually more like a cylinder. So it's not really like a four-leaf clover like I've drawn. It's more of a cylinder. Well, it's a cylinder that changes shape. It's a cylinder, but it's more kind of like a lumpy football kind of shape than it is a four-leaf clover. And the reason for that is because of the molecular orbital forming, which we'll talk about later. So it's because of molecular orbital theory, not from this. Okay, so one more lecture to go. We're almost at the end. Hooray!